Turbojet engine from Junkyard parts. A long time ago, at the very beginning of this channel, I built a small turbojet engine out of scrap parts. Since then, I have done several experiments with even smaller jet engines, with mostly unsatisfactory results. To fix this, I needed some bigger, better turbine components, so recently I stopped by an aircraft junkyard. A place where planes go to die when they are decommissioned or have crashed. With thousands of planes in various states of disrepair, the whole place was scattered with forgotten bits of turbo machinery half buried in the dunes. Picking through the piles of mangled metal in this post-apocalyptic place, I came across a couple lucky bits of turbine-related hardware, specifically an absolutely massive turbocharger that was possibly part of a piston plane engine. Judging by how heavy it was, it could have also been part of some sort of turbocharged ground service equipment that was also scrapped alongside the planes. Either way, I managed to take home this rusty, sand-filled fixer-upper for around $20. After unloading the rest of my salvage haul, I began to fully disassemble and thoroughly clean the turbo. I dumped out several pounds of sand from the internal compartments and spent much time getting the shaft and surrounding hardware unseized. Cleaning out everything from the bearings to the compressor housing was quite a time-consuming process, using rust dissolver and a wire brush on pretty much everything except the impeller, which required more gentle care. Once the restoration was mostly complete, I let everything dry out before reassembly. With the turbo back together, the impeller and turbine were free to spin now that all the seized oil and sand clumps were out of its system. To run this turbo as a jet engine, I would need a cooled oil system to hold the shaft inside the float bearings and regulate the core temperature. This was one of the major pitfalls of my first working turbojet, where the ball bearings got so hot that they became welded together. My first attempted oil system was also a long time ago with a much smaller turbocharger, and it was an absolute disaster that very quickly burned up its bearings and spewed oil before it even got a chance to start up. I hoped not to repeat this incident, so I tried to build something that I thought would be better. I also needed to build a separate combustion chamber that was large enough to handle the immense volume of air that it would need to deal with during operation. Because I'm learning to weld, I used an old air compressor tank that I cut open to make the outer case of the chamber. I welded it onto some base plates and used an empty fuel can as the air inlet, positioned to swirl the air through the inside of the chamber. I assembled the chamber liner out of a stainless steel ice bucket with carefully drilled holes of increasing size, with a total hole area slightly greater than the area of the inducer. This was placed inside the welded chamber and a gas injector was added at the top. The whole assembly was bolted to the turbine side and a rubber air pipe connected the compressor side. This engine works on the principle of the Brayton cycle, which is essentially a continuous version of what happens in a four-stroke engine. Instead of separate intake, compression, combustion, and exhaust strokes, all four happen simultaneously in different parts of the jet engine to produce constant power. The compressor side handles both intake and compression, combustion is held at a constant elevated pressure inside the chamber, and the turbine extracts the energy from the thermally expanded gases, with most of the energy going into powering the compressor. To make this concept work, everything would need to be well lubricated, so I added an oil system. Using a steel decoration sphere, I made an oil tank that could hold about half a quart of oil. To pump the oil, I used an automotive fuel pump that didn't give much pressure, but it was at least temperature rated. With an oil filter and cooling radiator, the oil system was ready to test. It's going through! It's absolutely going through. Dang it. After disastrously messy tests, I needed to fix several things, including using a larger return line and a more powerful pump. The constriction on the return line caused the oil to overflow through the turbine shaft seals, and the pressure was also too low to fully float the shaft in the bearings, causing excess friction and wear. To fix this, I replaced the return line and used a diaphragm pump and a salvaged oil regulator that could supply 60 psi volt to the bearings. This pressure is probably excessive, but at least the bearings would not immediately burn up. I also repositioned the chamber in the vertical orientation to avoid it filling up with oil in case of another internal leak. After a successful oil system and spin-up test, I worked on a couple other systems, including the igniter and fuel control. This engine was going to be controlled with an aircraft remote, meaning everything needed to be controlled by servos. The fuel system used a servo needle valve to throttle the flow of propane, and all relay channels were activated by servos, including the igniter and fuel shutoff. With all control wires and hoses installed, I wrapped them in reflective aluminum tape in an attempt to protect them from the radiant heat of the turbine case. I welded up a nozzle to focus the exhaust stream and get higher thrust. To start this engine, I used an EDF thruster strapped to the intake to push air through the system and spin up the compressor. With all systems looking good to go, it was time to give it a test. However, unlike almost every other jet test, I knew this would be particularly loud and have a high likelihood of exploding, so I dragged it all the way out to the middle of nowhere with nothing flammable for miles in all directions. This is where I tested my supersonic rocket Blink, which you should also check out. I prepped the engine, putting it on a steel plate that I thought could catch a small oil leak, and staked it down to stop it from flying away if it worked. I backed up to a safe distance and tried starting it up. Unfortunately, there was no ignition due to the spark plug not having a large enough spark gap and being in the wrong orientation. I doubled the existing spark gap and clocked the plug to expose the spark to oncoming gas. This time I had ignition, but no startup. The oil was also beginning to ooze out of the bearing ends already, overwhelming the collection plate. I spread some dirt over the plate to absorb the oil and repositioned the startup fan to be closer to the intake in a last attempt to get the engine started.
It's self-sustaining. All right.
This time, the engine started up almost immediately, slowly spooling up as I increased the fuel flow. When the engine speed had reached a maximum, I turned off the starter fan, and it continued to roar on the power of propane alone. For just over 4 minutes it ran, until I had to shut it off to save the bearings from running dry. As the oil heated up, the rubber hoses ended up bursting with small holes in half a dozen places. After the test, I cleaned up the test plate, making sure to leave no trace of oil at the test site. The engine was packed up and disassembled to inspect the condition of various components. Thankfully, the only thing that showed any sign of damage was the oil hose, and the bearings still looked as good as new. From the overall success of this test, I have several modifications to make to this engine, including all metal oil lines, a more powerful starter fan, and a much better oil cooler. I might even swap the float bearings for oilless ceramic ones in the future if I can do it without destroying the case. The oil is a nightmare to work with, and any way to avoid it would be a good idea both environmentally and for ease of handling. I also need to collect thrust data to determine its true performance, because sustained combustion doesn't always mean there's very much thrust. I hope to continue work on this engine, and with many improvements, be able to get usable thrust. Oh, no. Glad I have the tray. Dang it.